class. This is number 5 and 7.1. And so it says, the manager of a company retail, the manager of a computer retail store is concentrated that is concerned that his suppliers, have been giving him laptops that with a lower average quality. His research shows that replacement times for the model laptop of concern are normally distributed with mean 4 years and a standard deviation of 0.6 years. He then randomly selects 34 laptops sold in the past and finds the mean replacement to be 3.8 years. So yeah, they're expected to replace them in 4 years. So 3.8 years, is that really showing that that these are less qualified, less quality laptops? So let's look at that. So you find the probability that 34 randomly selected laptops will have a mean replacement of 3.8 years or less. So to kind of understand the mean, and what we have to do is we have to find this probability, we have to find the area under the curve of this, and the curve is called the sampling distribution of the mean. So what scientists did is, let me show you the simulation, is they did a simulation. They pretended they had a distribution with a certain frequency. Let me show you. Let's just pretend this is the frequency distribution and the original population of, that's how many, you had some laptops that, I'll just say laptops right now. They needed to be replaced really quickly, and others you didn't have to replace after 10 years. And of course, the ones that last a really long time were very, very few. That's why the height of these rectangles off to the right here are really low, because people don't keep their laptop for very long. And then people don't have to replace it very quickly either. So the small numbers here are very low, and it's the medium numbers in the middle here that are the numbers that occur the most. So the taller rectangles are around that one. But anyways, if we have a frequency distribution like that, and what we can do is we can simulate, the computer can just make, just randomly pick things from our population, and the computer is good about, well, if there's more computers with a certain type of quality that they last for 4 years, then the likelihood of me picking one like that is more, so they are good about picking it according to the frequency distribution, and making a sample that is representative of frequency distribution. So when they do a sample, there's actually more, they're more likely to pick ones that have higher frequency. So anyways, so they do a sample, and what happens is they pick 5 different, now here they're doing a sample of 5. And this is just an example. They did a sample of 5, and then they took the mean of those 5, and then they put the mean on this new distribution at the bottom. See, if we do 5 more, then you get a new mean. So we're doing at the bottom here, we do a sample, and then we record on the very bottom graph the mean of that sample. So we pick 5 numbers. Those are the 5 gray numbers that just dropped, and then 1 mean is calculated from those 5 numbers. And so we can do it again, 5 new numbers, and we find the mean of those numbers, and then it's calculated at the bottom. And we can do it again, 5 more numbers in a sample, and then find the mean of those. So it's calculated at the bottom. Now let's go ahead and do 5 at a time. So that gave me 5, I did 5 samples, and that gave me 5 new records for reporting the distribution of the mean. Now we can jump and we can do 5 more, and we do 5 more. So it's building a and it does 5 samples and automatically calculated the mean of each of the 5 samples, and it added the 5 down here in this distribution. So we can do more and 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 more. And as we do more, we're gonna get the shape of this sampling distribution. And if we do like 100,000 more, look what all of a sudden happens. Look at the shape. Notice how the shape of this sampling, this is called the sampling distribution of the means. And because it is the frequency distribution of the means. So notice how this is not as wide as this gray one at the top is the original distribution, is really wide, and this distribution of the sample means is a much thinner and tall, but it's not necessarily taller, I suppose, but just thinner. So that's what we should expect always to be the case. Whenever we have a normally distributed original distribution, and then we look at the sampling distribution of the mean, it always is just, it kind of looks bell-shaped as well, and that the standard deviation is smaller. And we can actually calculate the standard deviation and see the original standard deviation was 5 up here, and then the new standard deviation of this sampling distribution of the sample mean is significantly lower. It's 2.24, and there's actually a formula that will predict what this sampling distribution will standard deviation will be. And notice the mean of the original population is still the mean of the sampling distribution. For sure, you see that's this case, but the standard deviation changed because it's a thinner thing. Okay, so that was to help you understand so we need to look at this distribution and find this distribution, find the area under this distribution in order to find, whenever they talk about what's the likelihood of me getting a mean from a sample back with some characteristic, we need to think about the area underneath the curve of the sampling distribution and not of this the blue sampling distribution here and not of the original gray, okay? Because we only find the probabilities of one event happening, like me picking a random one thing happening with the original distribution. But if we wanted to know what's the probability of me getting a sample of 50 things happen, 50 with a sample with a mean of something, then we have to use the sampling distribution of the sample mean, right? Okay. So let's go back to this problem. So like I said, we need that blue, and there's a formula for the standard deviation of that blue distribution. And all they say is, well, they said the mean of this new sampling distribution, which they use as a X bar, it's the same as the mean in your original distribution. So whatever they tell us is standard deviation, we're going to use it. So his research shows that replacement times for the laptop have a standard deviation of 0.6. So that's going to be our standard. That's going to be the mean that we use. I'm sorry, the 4. I'm sorry, not standard deviation, the 4. 4 is the mean. and 0.26. We're talking about the mean right here, mu. The standard deviation of the sampling distribution is equal to the original standard deviation divided by the square root of n. So that is the original standard deviation, which here is 0.06, but divided by the square root of n. And they said that the n is 34 because there's 34 random. That's the number of sample people. And we just calculate what that is. And then once we have a mean and standard deviation, then we just go to our calculator, calculate underneath the curve. And if we look at this curve, it has a mean of 4 and 3.8 is like over here. So we're trying to find like this area. Okay, so let me find a calculate. Well, actually, we don't have to calculate that, right? Okay. We don't even have to calculate that. All we do is, let me show you each step. So I go to stats, and then I go to distant distributions, get a normal distribution. And then for the mean, I put 4. And then for the standard deviation, I put the 0.6 divided by the square root. I use that symbol, square root of 34. And then there I go. I pick CDF. And then I need to now it's greater, less than. This is 3.8 years. Okay, find the probability that 34 laptops will have a mean of time of 38 years or less. So we need to find the probability of that or anything less. So what we need to do is this. What interval are we looking at? We're looking at any number less than 3.8. So the large number that we hear is the 3.8. Right, so any number 3.8, 2.8, 3, 2, 1.8, all of those down to negative infinity are what we need to be calculating. So there's our answer, the 0.0259. I think if you are using a TI-84 calculator, I believe, it will not, I think they tell you a lower bound and upper bound, I think, and instead of negative infinity, because that calculator doesn't understand the negative infinity, so you have to put in negative, like e to the 99 power or something like that. I think that's usually what I put in using my calculator. I put the lower bound, if I were to use a TI-84, I would put the lower bound is 1, negative 1, because it's negative infinity. Negative infinity, well, you really need to put in as a lower bound is negative infinity. But the upper bound, because you want everything smaller than 3.8. So the upper bound, your highest level is 3.8, and then the lower bound, you're just trying to say, well, everything less than 3.8. So you put the lower bound is negative 1. E to the 99. And I think on the calculator, it's not the number E, you'll see EE. Look for a button that says EE. That's what you need to put in there. And then, so that's how you'll enter it. But the class calculator, it's even easier. You don't have to worry about that. You just put this negative infinity in, and that's exactly what we need, negative infinity. So everything smaller than 3.8, which would be, reaching to everything to negative infinity. All right. Well, I hope that you found this really valuable. I hope you understand this. So our final answer here was this 0.0259. Well, actually, but let's double check it. At 0.026, they say, or 0.0259, either one. And then they asked, based on the results above, does it appear the computer has been given the computer score has been given lab tests with lower average scores? So if this is unlikely to occur, then most likely these are bad.
Mommy,
Okay, so the probability of this occurring, of us getting a sample of 34 that has 38 years or less, is 0.062, 0.0. So if we turn this into a percentage, you know, like, or if we turn it into a fraction, okay, so what we can do usually, what a good way to do this is turn this back into a fraction. You know, so this is a really cute way to turn anything back into a fraction, is you can make the little dot in the decimal into a lowercase I by drawing a line below it, and then draw a line through the decimal, and then any number that's like to the right of the decimal on the top, you put a 0 under it. Okay, so this becomes like 26 out of 1,000. That's the likelihood we have here. And it might be even more understandable if you just round this to 0.03. And we make that into a little I, lowercase I, and then draw a line through it, and then I get 2 zeros. For every number to the right of the decimal on the top, you draw a 0 below it. So this is 3 out of 100, basically. It's a little bit more understandable than 26 out of 1,000. It's 3 out of 100. So we would expect this result to happen only 3 in 100 times, with the given belief that the distribution is the average computer will last 4 years. Then, so this result, these are unlikely. This is a very unlikely result if the computers are on average lasting 4 years. So because an unlikely result, maybe it's evidence that maybe the computer, this is wrong. Maybe the computers are not lasting 4 years, because you know, this result is very unlikely to happen. And like doctors kind of use this if something's very unlikely to happen, they just kind of, well, unfortunately, I feel like they assume that it doesn't happen, because it's very unlikely it just doesn't happen. So they're saying that this does not happen. You would not get a sample of 34 computers to have a mean replacement time of 3.8 years, unless the average computer itself is close to having a mean replacement time of 3.8 years. So so yeah, so this is evidence that probably the computers are less qualified. They're lower quality. So I would say yes, the probability of the sample shows there's a possibility that the owner is given lower average quantity. Yeah. Okay, we can just check our answer. And usually, you might ask, well, how low is low? Usually we say like 5 out of 100, or smaller is like less, is not very likely, is unusual. Oh, so let's see the answer here. Yes. Yep. All right. Have a great day, everyone. Bye.